Okay. All right. Good morning, everyone. We're going to try to do this quick and have a 60-minute talk by Professor Kyunghyun Cho. And before he starts, let me introduce a little bit about what we're doing as this collective effort here. So we have something called the KAIST-NYU Center for Inclusive AI, which we just initiated like very recently, like a month ago or less than a month ago. And it's part of this university-wide effort between the two universities. And it actually includes research and education. And the Center for Inclusive AI is one of 7 research centers. And we created this to foster collaborative research among the many very active and excellent researchers at KAIST and NYU, including Professor Cho that we have here today. So I was thinking about what to do in this research center, and because we have this whole crazy thing going on with ChatGPT and large language models, I thought that's a great way to start this because we have Kyunghyun and we also have a few others that are excellent in this research area. So today we have Kyunghyun talking, and then on Friday, March 3rd, we have He, who is one of the very young but very up and coming researchers in this language models space. And then next week, we have James and Minjun, and this actually is going to be hybrid. So we're actually going to do this in person in Seoul, I think, and we're going to try to broadcast this too, so people can watch online. And today's talk is being recorded. If you are concerned, you may, not show yourself on video. It looks like it's just me and Kyunghyun showing on my screen, so hopefully that's what's being recorded. If you have any questions, please do use the chat, and I don't know. I will try to watch the chat, and if there is a question that needs immediate attention, I will. Okay, I'm going to try to mute some people who are. All right, there's a lot of noise coming from somewhere. Okay, so if you are not muted and there's some background noise, please do mute yourself. All right, so that's the schedule. And now I'm going to stop sharing. And Kyunghyun, if you want, you can start sharing your slides. I'll try to figure out who's
I think you can mute everyone. Yes.
Okay, I got it. All right.
Okay, got it.
Oh, you can.
Well,
okay.
Thanks. Yeah.
Okay, let me do a quick introduction. Hold on.
Okay.
So we have Kyunghyun, who is an alum actually of KAIST. So we're always great to have him giving his talk. He's a faculty at NYU, and he's also not sure what the title is at Genentech. Okay, let me read this. So CFAR Fellow of Learning in Machines and Brains. He's a senior director of frontier research at the prescient design team within Genentech Research, where he's trying to do research to save lives. All right. He's won numerous awards. He's done lots of really great and important service in this research field of machine learning and natural language processing. He has recently won Samsung Hoam Prize in Engineering in 2021. And great, let's give him a round of applause, virtual applause, to welcome him. And
thank
take
you.
it away.
Yep. Thanks for the generous introduction. And I thought what I talked with Alice about was to make this talk or more of a session more closer to discussion than just a one way, let's say to talk. So I thought I want to talk a bit about what autoregressive language model, this particular technology that has been fueling these advances or the things that we have seen, they're fueling the level of the excitement that we have seen with the ChatGPT and whatnot. And then after that, if there's anything that you want to discuss about, I'll be happy to chat about it. Fortunately, I started to work on this direction of, let's say, building a neural network for the machine translation as well as the language models already from, let's say, 2013 or so. And then I kind of, let's say, was ramping down my own research in direction. Well, who knew this was going to be like this big? So I have some, let's say, thoughts on what are the kind of, let's say, basic building blocks behind all these, let's say, large-scale language models that are making splashes these days. And then I'll be happy to give you a bit of a both, the exciting as well as a grumpy takes on a lot of different aspects if you have any questions there. But let's get into some of the basic, let's say, aspects of the so-called autoregressive language model. So autoregressive language models or any kind of, let's say, large-scale language models that you see these days, including ChatGPT, and then supposedly Bard. There's a Llama that's been released by Facebook AI Research just earlier today. And then there are numerous, let's say, different types of the language models that are being released by the different companies. But then all these language models, if you just open it up and then look underneath, then what you see is that there's literally one equation that actually drives all these different language models. That is that we are going to represent, or we're going to build a machine that is going to compute the probability of any given sentence as a product of the probabilities of the next word. And then this is often referred to as next word prediction. Now, given what has been generated so far, what should be the next word? And then by looking at what should be the next word over and over, we end up with the entire text snippet. And then this machine is able to score any given text snippet as well as be used to produce any of these text snippets. And literally, this is the most important equation that underlies all these language models. And then in fact, if you look at it carefully, and then if you recall from your high school, in the mathematics course in high school, at least in Korean high school, near the very, very end, there's a bit of a chapter on the statistics and probability. And then this equation actually shows up there as well. So really, this is one of the most fundamental concepts in probability theory. And then this is one of the most fundamental concepts behind this large scale or the successes of the large scale language models. So let's say I want to compute this probability. Somebody gave me a large amount of text, and I want to build this language model. What do I do first? Is that we're going to build a gigantic table. Now on the left side, I'm going to write what has been written down so far. And then on the second column, I'm going to write which word follow this prefix. And then for each and every combination of the prefix and next word, I'm going to write down in the third column how often the combination appeared in this large amount of corpus. And if I can actually build this table large enough and extensive enough, then I can easily compute this probability given any text snippet, because I can compute the probability of the next word given all the previous words by looking through the entire, let's say, table. Now, if you recall a bit, if you're a computer scientist, then you know that okay, this doesn't make any sense. This table is going to be too large. But let's just assume that our table can be as large as we want. And in fact, that is one of the things that we are seeing with these large-scale language models. Why are they calling them large? Because they are not large because they are just large, but they are large because they're as large as the training data that we use to train these language models. So in fact, this must be what is going on inside, because this is exactly what we need in order to implement that fundamental equation that I showed you in the previous slide. Now, once we have this table, it's really straightforward. Generation is really easy. What we're going to do is that we're going to look for a row initially that has nothing on the first column. And then we're going to look at all the rows that have nothing in the first column. And then among all those, let's say, rows, retrieved rows, we're going to look at all those associated counts and normalize them so that we get the probabilities. And then according to probabilities, we're going to choose one of the rows. Now we have the next word. Then we're going to now look for all the rows where the first column corresponds to this selected one word. And then we retrieve all of them. Again, normalize the count, make it into probabilities, and then sample accordingly. So really, this building a table turned out to be the key to building this kind of large-scale language models. So the idea is count and retrieve. This is exactly what any kind of language model that is autoregressive needs to do in order to be a language model. We look at a large amount of data, we count all these combinations of the prefix and next word, and then based on this table that contains all these counts, we need to do the retrieval in order to compute the probability of any given text snippet and also to generate text from that. An interesting thing is, this is not a new idea at all. Already in 1950s, Claude Shannon of the information theory wrote a paper, really interesting paper, talking about, can we actually compute the entropy of English? He was really into putting everything into the words of information theory. He wanted to know how much information does English as a language convey. And then to do that, what he wanted to do was to see, given a prefix, how many possible next words there are, and then how many bits we need in order to predict or compress what comes after. And then you do that for every sentence in English, then what you end up with is that the amount of information that is contained within English as a language. And if you look very, very closely at the equations 1 and 2, what you realize is that the equation 1 is exactly the equation that I actually showed you at the very beginning, except that we're looking at the log domain now. So this is not a new idea. The fundamental concept of how we can actually compress the entire corpus by counting how many bits we need in order to represent them is from, let's say, 60, 70, 80 years ago. And I'm pretty sure Claude Shannon was not the first one to think about it. A lot of people were thinking about this kind of thing. Then if you go all the way back to, let's say, Renaissance time and whatnot, there were all those automatons that were able to actually write something automatically without a person in it. And then those are all based on a somewhat statistical, let's say, principle that is exactly the same as the principle that drive all these large-scale language models. Now, of course, we don't build these tables ourselves. No one builds these tables ourselves. Now, well, of course, until about, let's say, 2012 or 13, we used to build these tables ourselves. And how to build these tables efficiently and effectively has been a long-standing research question. But already by the end of the 20th century, Joshua Benjo and others who have been looking into the kind of neural network in order to represent this data realized that, well, do we really have to build a table? How about instead of building a table explicitly, can we replace or approximate the entire table with a single neural network classifier that's going to minimize? I have a loss function here. If you are familiar with the deep learning or the machine learning, you're going to see that, okay, obvious, yes, it's a cross entropy or not. But if you're not, you don't have to worry about it. This is, again, exactly same equation as the first equation I showed you on the first slide, as well as what Claude Shannon wrote down in his paper from 1950. That is that I want to train a neural net classifier to be able to predict what the next word is going to be, given the prefix, that is that all the words that came before. And then we train a neural net to maximize the predictive accuracy on the next word prediction. And then this is essentially identical to trying to build this table, but in a way that is not explicit. We're going to let stochastic gradient descent, as well as a lot of the same mechanics of the machine learning to figure out how to build this kind of this table-like representation internally in a high-dimensional real-valued vector space. So then what that means is that because what we are minimizing in order to train these language models is equivalent to building this table to build a language model, one might even say that the neural language model really is just learning to count. And that's really nothing magical there. And then in reality, if you think about just exactly the training corpus, that's exactly what is happening. Our language models tend to be as large as, if not larger, than the training corpus, and certainly larger than the information content or the number of bits that are needed in order to compress the entire thing without any loss. So it can really create this table for us. We don't have to make our table, but the neural net training is actually creating this table. Okay, it's just really learning to count, nothing really magical here, right? But then the thing is, learning cannot only be about counting. Or building a language model cannot only be about counting, because if we make the table, the count-based table that I showed you earlier, without a lot of, let's say, bells and whistles, this table will not generalize. Now, what do I mean by generalize is that based on this table, this language model will not able to assign a non-zero probability to the text snippet or the sentences that were not seen during training time. So what this table does is this table is a very accurate picture of what is in the what we call training corpus. So what has been written already by the time of training this language model, but it's so accurate or exact to the point that according to this table-based language model, any text that was not in the training set is impossible. So for instance, let's look at this one example. A lion is chasing a llama. This sentence had never been written until about, let's say, 2016, when I was creating my lecture note. And then I did check the Google and everything. It really had not been written by then. But I'm pretty sure now, this sentence is not really impossible in the sense that I've written it down. And then these slides and everything are online, so Google has already indexed it. But let's say we are in still 2016. The probability of a lion is chasing a llama can be decomposed into the product of all these next word probabilities according to this autoregressive paradigm. Again, sticking to the very first equation from this talk. So we're going to look at the probability of A at the very beginning, probability of lion following A, probability of is following a lion, probability of chasing following a lion. All these probabilities are somewhat non-zero. However, the probability of llama following a lion is chasing up is zero. It never happens. First of all, llamas and lions don't even live in the same continent. And then in zoos, they're going to be separated from each other very, very far away from each other. So what that means is that according to this kind of table-based language model, the probability of the entire sentence, a lion is chasing a llama, is going to be zero. But that cannot be the case. Why is that not be the case? Is that if that was the case, I would not have been able to write down this sentence myself. But I somehow have been able to written it down. And then all of you who may not even know how llamas look like can imagine what the meaning of this sentence is. And then that is a generalization. That is a generalization that we need, is that the language model should be able to assign probabilities that are non-zero to the text that is unlikely or that never happened before. An interesting thing is these neural net language models can generalize. Although we are building neural net language model in the same way as we built the table-based or the count-based table, let's say language model, these language models that we built with a neural net can generalize. And then the reason why it generalizes is because it not only memorizes the building a whole table, but it also compresses. Because of the so-called implicit biases of the stochastic gradient descent or the implicit regularization, as well as a lot of explicit regularization techniques that we use, all of which are kind of important, but not really important for this particular, let's say, discussion. Because of that, these neural nets are heavily penalized or encouraged to compress the data as much as it can. And how do we actually compress any kind of large amount of data? If you are, again, a computer scientist or the students in computer science department, you probably learned that from the algorithm course or whatnot, or the discrete mathematics, right? So what we're going to do is that we're going to look at similar patterns and then trying to build a small table that's going to represent those similar patterns with a small number of bits so that we don't have to repeat it over and over. That is, we're going to cluster similar inputs, and then that's how we're going to save number of bits. We can think about all those Brown clustering, latent semantic analysis, and whatnot. And here the similarity is implicitly imposed by similarity in the context. That is, as both the prefix as well as the next word. Now, very, very vague. Let's look at one example that I made it up again. So let's say we have only 3 training examples. There are 3 teams left for qualification. 4 teams have passed the first round. 4 groups are playing in the field. And then out of this text, we're going to look at only predicting the next word given the previous word, a single word. So 3 teams, 4 teams, 4 groups. Let's just look at those 3 diagrams or the phrases. The question I want to ask here is that how likely is groups, the token groups, followed by token or word 3? Now, how would this neural net do? If this neural net sees that, okay, there are 3 teams, then what it wants to do is that it's going to map these 3 into a point in this continuous vector space from which it can decode out groups. And then next, it sees 4 teams. And then it's going to try to put this 4 near 3 because I already know that from this particular point that is near where the 3 was mapped, I can easily decode out teams. And the next 4 groups is seen, and neural net is going to know that, well, 4 was already mapped to this particular point that is next to a point to which the 3 was mapped. Now, let's try to read out groups from nearby points. And then in the test time, when it sees 3 groups, it knows that the 3 groups are not unlikely, but it's very likely because 3 is going to be mapped to the point that is very near the 4 was mapped to. And then from there, this neural net can decode out either teams or groups. Now, this is the power of the continuous representation. Now, suddenly, due to this training with the neural network on large amount of data using a continuous vector representation, all these subtle similarities among the textual representation or the text snippets are automatically captured in the process of compressing the entire training data. So let's see. So it turned out learning is not only counting, but also compressing. So what it does is that it's going to start from a large table that summarizes the entire training set. But then what this neural language model does is to compress it so that the number of bits it uses in order to encode this number, the entire training set is minimized. And then that's where the generalization comes in. But then if you think of, okay, so it does counting and compression. Where's the magic here, right? Still doesn't look that magical at the moment. But it turned out that this process of compression is where something that we don't know really happens. And then of course you had what is magic? Magic is really nothing but a set of questions that we haven't answered yet. So then we have to think about what are the questions that have not been answered yet. And then in this particular magic, there are 2 sides. One is compression. What is compression? Is to assign no probability to probable instances. And then generalization is assigning a probability to impossible instances. So what that means is that in the process of compression, because our model is not perfect, it's not a perfect compression machine, it's going to be lossy. It's going to lose some information. And what it means by losing the information is that it won't be able to assign the entire probability mass. That is just 1, right? That's what probability theory tells us. So there's a probability mass of 1. It's not only going to be spread through the training examples, because that's going to be a perfect memorization, perfect compression, but the probability, some amount of probability is going to spill over to non-training examples. So some of the text that was not seen during training will receive some probability mass. And then that's the big question. Okay, what are the things that language models choose to ignore? As I said, these probability mass should have gone entirely into the training examples, but because of the imperfection of the compression algorithm or the learning algorithm, some of the probability mass will be lost. Now, what are some of the training examples that are going to be forgotten? It turned out this kind of compression does not lose information uniformly across training examples. Often some subset of training examples are lost more so than other subsets in the process of compression/learning. And it's really, really difficult to characterize what are these examples that our model has decided to ignore on its own by learning as well as it can. And then there's been a lot of studies during the past few years about it, but the fact that we are working now with the billions, if not trillions of the examples, and working with the models that has a billions, if not, I guess not trillions yet, but billions, if not hundreds of billions of parameters, it makes it really difficult. And then it has a really potentially undesirable, let's say, consequences, because some of the things that we really wanted language models to remember might be forgotten here. And second question, that is the other side of this coin, is that we don't really know what are the things that language models prefer to assign these excess probabilities to. So where the examples here are not the training examples, but the unseen ones. And then we really don't know, because it's a very difficult question to even ask correctly in this kind of high dimensional space. And then it's also very consequential for these large scale language models, in particular, if you want to deploy them in practice, because of all those issues of the hallucinations, as well as the factually incorrect generations. So what are some of the factually incorrect texts does this language model prefers put the excess probability on? We really don't know how to characterize them. What are these phenomena of hallucination? Can we actually characterize what are more likely to be hallucinated? We actually have no idea about them. But then so far, it's all about just scoring, right? So I talk a lot about the probabilities, but some people might say, well, I don't really care about probabilities, because as far as I can tell, when I use ChatGPT, it just tells me the answer, never tells me the probability or anything like that. That's actually absolutely true. I went through this because generation implies that we have this kind of table-like representation underneath it. So how do we generate it? I already talked about it earlier. The idea is that if we start from the empty prefix, or we're going to start from the prefix that we give, we often nowadays call it as a prompt or question. And then we're going to look at the rows that correspond to this prefix or prompt, retrieve all of them, look at all possible next words, sample one of them according to the counts. Once I have sampled next word, I'm going to append the next word to the prefix, and again do the retrieval, get the probability distribution over the all possible next words, and then sample from it. You just repeat it over and over. Very straightforward, but it turned out that the number of rows in the subtable, so given a prefix, I'm going to look at all the retrieved, all the rows that match to it, and then trying to normalize them and sample from it, and on and on and on. This process is still too expensive. We have to dramatically reduce the number of rows from this exponentially many rows to the constant number of rows. Unfortunate thing is that we actually don't know how to do that well. So we have to be a bit somewhat approximate and heuristic driven. And then we use various types of the approximate decoding algorithms. Sometimes you may have already heard about the terms like the beam search, 3D decoding, ancestral sampling. Well, ancestral sampling is exact, so let's put that aside. Top case sampling, top piece sampling, temperature-based scaling, all those things. But all these terms essentially are our way of conceding that we actually don't know how to do the decoding properly. We have to somehow come up with a way to reduce the amount of computation we use in order to generate. And then doing so, it turned out that a lot of interesting, let's say, phenomena happens. What do I mean by that? Is that these language models not only have their own, let's say, preference toward what kind of sentences or the text should receive a high probability, but these approximate decoding algorithms also choose, or they have their own tendency or the preference to choose particular type of the text. So so one of the weirdest things that you often find with this kind of autoregressive models is that these autoregressive models tend to assign huge amount of probability to extremely short text snippets, often of length 0. But then by mixing it with the 3D decoding, which assigns a impossibly higher probability to infinitely long sequences, such as the one that repeats forever and ever and ever. By using these two together, we often end up with the texts that are well-formed and of a reasonable length as well. So it's one of the biggest mysteries that I've been actually studying ever since like 2018 or 17, and still I haven't actually resolved it. And then whenever I was working on this, everyone was telling me that, well, we scale the model up, we scale the data up, this issue is going to disappear automatically. But it turned out that the Bing's, let's say, ChatGPT search engine also has this issue of the repetition. So it looks like this is a question that still requires us to, it requires our effort to answer as well. So let me just wrap it up quickly. So what we do with this kind of large-scale language models is really just count, compress, and prune. So we count because we need to know how often a particular next word follows a particular prefix. It has to be done. We compress because we regularize learning in these neural language models. And then we have to prune because we cannot use the exponential amount of time during the time of generation. And then what is happening is that this compression part and then pruning part are where this kind of magical behaviors that we see these days happen. And then interestingly, those are extremely well-defined, let's say, mechanisms by which these models work. So instead of, let's say, thinking of it as from the perspective of, oh, this is some of the awesome things happen, but it looks like that these are the things that we can actually analyze and also use them better or build a better algorithms for. And then I think that's probably the final slide of mine. Okay, probably not, but this is really the final slide, because at the moment there is a bit of a, I tell my PhD student, my own PhD students, say, okay, there is a bit of a defeatism. Is that a lot of, let's say, PhD students or the researchers who have been working on natural language processing as well as machine learning all feel somewhat defeated because they feel like, oh, well, whatever I've been doing over the past, let's say, 20 years, seem to have been solved by ChatGPT, because my undergrads can just type in the question that I've been pursuing for 20 years, and ChatGPT gave the perfect answer. So there's a bit of a defeatism, but I don't think we should have that, because this is, I think, it's just the beginning. And then whenever there was a point at which any particular, let's say, computer science or the algorithmic, let's say, technology was considered mature and can be easily deployed and solve a lot of problems, there has always been the next one that was way, way better. So I wouldn't worry too much about it. And this is what Tomasz Mikolov said in 2021. And he, I believe, is nowadays working on artificial chemistry, whatever that means. And then that's really the end of my whatever I have prepared. So if there are any questions or the comments, I'll be happy to actually talk about them together with you.
Okay, clap, clap, clap. As always, Kyunghyun gives great talks. So if you have a question, please do type in the chat. I think he may take questions written in Korean.
Yeah,
he's
fine.
Fluent.
Spoken, written, either, yes.
Yeah. All right. And you can also raise your hand and I will try to watch. Oh, James has a question. But before, I do have to ask my question, which, so you talked about several issues during this talk, and then there's some issues that you didn't explicitly mention, but we know that they exist in language models like ChatGPT. So the ones you mentioned, like lossy, right? So losing information, and then sometimes generalization seems to, it's hard to say whether generalization causes hallucination, but there is that big problem of hallucination. And you also mentioned repetition. And this more general problem of not being able to control the length of the output. So among those issues, and then there's like the bias and all kinds of other issues. Among those issues, what do you think are most important or significant or difficult? And can any of them be resolved or at least mitigated?
So I think the easiest one that we have made a lot of progress, I mean, there's a community is getting the length correct. That one, I think we're actually doing it better. Just because that was the most obviously, most apparent issue that we saw already from, let's say, I don't know, 2016 or so. So I think the length-based issue, I'm still working on it. Some of my students are still working on it. I think we're going to get it kind of, let's say, completely nail it down at some point soon. But then when it comes to hallucination, because the hallucination is not really hallucination. That's, from our perspective, models are hallucinating some weird stuff. But that is just what generalization is supposed to be in terms of generation. Because if there is no hallucination, what it means to actually generate something that is not seen during training time. So in a sense that I believe that the hallucination is not really the, technically correct term to use in this particular case, although I use it every day.
Mm.
So then the question is, what are some of the design choices that we have made for, let's say, building these neural networks or designing these learning algorithms that makes particular types of the inputs or the outputs preferred? So that kind of, let's say, patterns of generalization, I think, should be studied. But that one, I'm very, very skeptical that we'll be able to do that well. Now, this kind of repetition is one of those things. Repetitions turned out to be easy just because it's connected very much with the length issue. But anything that is difficult to quantify as correct or incorrect, like the length is very easy to quantify as, okay, incorrect, correct. But otherwise, it's going to be very difficult. So it's almost like the learning theory, like the plus here.
I see. Okay. Do you think, one last question for me, do you think that has to do with the way that neural networks work? Do you think that if we choose to use a model that's just really different from the neural networks that we are using, would that be able to at least show us what's going on?
No, I don't think so. I almost feel like the one of the reasons why I think transformers are really powerful and that we use transformers everywhere nowadays is because they are actually the culmination of the major advances that we have made as a community over the past, say, 3 decades, starting from the stochastic gradient descent to, let's say, LSTM or those shortcut connections like the residual connections, attention, as well as various normalization layers and whatnot. So it's not that transformers are special, but the transformers are the ones that we know how to train and scale it, both in terms of the memory, computation, and data. So in that sense, the dramatic change to network architecture is going to be very difficult to achieve. It's going to be somewhat on top of this because these things are just there, not because we wanted them to be there, but those are the things that actually supports this kind of scaled up learning. But then what I believe is that but this is just a parameterization. So how do we compute the conditional probability of certain output given the input? But then the idea is that, okay, what is the right loss function to use? What is the right kind of inference algorithm to use? We are very much stuck with this kind of statistical, let's say, paradigm of learning. But learning doesn't have to be only statistical. We can actually go beyond. Maybe we can be a bit more causal, or we can be more, let's say, mechanistic. So all those different things that we can do, but I'm not entirely sure if the parameterization is the one place that we're going to see much of the improvement. But I'm known to be wrong as well. So yes.
Okay. All right, so let's get to the audience questions. So James asks, what are your thoughts about non-autoregressive decoding and its relation to factual generation from the mode? Perhaps we can ground key info first and fill in the gaps later.
Yeah, thanks for the great question, James. Yes, I'm a big fan of the non-autoregressive, the models. Ever since like 2017, that's been always my kind of pet peeve, and I use it everywhere. Never succeeded in using them successfully so far. But yes, non-autoregressive decoding, or more like this kind of iterative generation or the iterative refinement. We have, especially in the text generation, we've been looking into it ever since, let's say, 2016 or so. And the audio generation, people have been looking into it. And nowadays, all these successes in image generation using diffusion-based models are all in the family of iterative refinement. Now, iterative refinement does have a number of advantages. So for instance, it probably requires, well, that's our hope, fewer number of iterations than the size of the image or the configuration that we generate, assuming that the computation can be parallelized. That's just because at the moment, autoregressive model always requires at least a linear amount of computation or the generation, number of steps of generation. On the other hand, with the parallel, looking at all these pixels all together might get us, let's say, number of steps of generation. However, what we see these days is that when the dependencies between these pixels or the input dimension is extremely strong, so far, autoregressive model seems to be the best way to go about. The reason being that these dependencies are all kind of somewhat translation invariant. So you take any consecutive, let's say, pixels or any consecutive words, they are extremely strongly dependent on each other. But if you And even if you translate it by few, let's say pixels or whatnot, the dependency stays same. And with the autoregressive models, what we do is that we use the same model that is very powerful at every location, which kind of gives it extreme statistical advantage to have modeling this kind of, let's say, data with a strong interpixel dependency with a strong, let's say, translation invariance. Now, on the other hand, with the kind of diffusion-based model, what is the right kind of dependencies across all these pixels, across the generation step, is still unclear. And then that's the reason why in images where the pixel-wise dependencies are somewhat weak, because even if you make a couple of mistakes in the pixels, no one really notices it. But in text, one mistake kind of, let's say, breaks the entire thing. That's where the so far autoregressive model has triumphed over the non-autoregressive models. So we'll see down the road. Yes, I'm still, working toward that one. It hasn't been too successful over the past 6 years, but maybe the 7th year is a charm. Yeah, maybe.
Yeah, good luck. So Teshik asks, in your opinion, what would be a good solution to fix the incorrect answers by LLM?
Oh, incorrect answer. Okay. Well, so I guess one of the most important thing to realize, I was talking to actually one of the postdocs here earlier, not today, but actually last week, early part of the last week is the thing. So a lot of students, including the postdoc, they come talk to me about can we actually use this large scale language model by making 2 copies and then use one as a generator and the other as a verifier. And I had to tell them that that cannot work. Because if there is an exact symmetry, the verifier and generator are actually the mirror of each other. Because verifier is a score and the generator is a score maximizer. So if the score maximizer is maximizing the score that is used by this verifier, then of course, always whatever has been generated will be scored well by this verifier. So verifier and generator won't actually do anything together. They won't actually agree on each other forever, meaning that the correctness cannot be determined in this way. So there has to be some kind of information asymmetry between verifiers and the generators. That's probably the reason why a lot of people are using some kind of, let's say, human feedback in order to tell whether the generated snippet or regardless of whether it was generated by humans or the machines, are better than other types of the generated text. And then that kind of, let's say, binary preference can be useful for creating this kind of asymmetry. Or in the case of, let's say, simple, let's say, way to tell whether the generated text doesn't make any sense, such as the excessive number of repetitions, we can just build a rule-based system in order to tell whether the generated ones are preferable or not, and then use that to fine-tune the model so that the generator becomes less prone to generating all those, let's say, weird-looking, let's say, text. But unfortunately, what this means is that it's very unclear whether we can actually come up with a way to handle this issue other than introducing some kind of information asymmetry that is very much dependent upon the problem that we are solving. And it's connected to the earlier question by Alice as well, in a sense that because we don't know the pattern of generalization, that is that we don't know what are the subset of the text that receive a high probability due to the lossy compression, we can't really say what are correct or incorrect. If we could say that automatically already, we would actually train it to not say anything incorrect from the beginning. But unfortunately, we're not there yet.
Yeah, a related question from Kunu Park is, why do they not know what they don't know? Like, so can we talk about confidence? Like, do the models feel more confident about an answer versus another?
Right. So it's okay. So the models, when they so let's put it in this way: when the models are trained really, really well, in a way that they are regularized perfectly, and then in fact this model family does include the true generating process. And then if we had enough number of examples, then these models will be calibrated well so that we can in fact use the actual probability coming out of these models as a way to, as a proxy to the confidence from by this model that is in fact reflecting the reality, whether it's going to be correct or incorrect. Now, unfortunate thing is that none of these three is satisfied. So we don't know. We're pretty actually sure that the actual language generation process, that is us, is not in this transformer parameter space. And then we are pretty sure that the learning algorithm is imperfect. So we're not regularizing learning correctly. And then we are also pretty sure that the amount of data we have is not large, nor is representative of the human data generating process. So because of that, the calibration becomes the probabilities we get out of these models are not well calibrated. Now, there are some papers, recent papers, talking about how they are actually reasonably well calibrated in a so-called fuchsia learning setup. But unfortunately, checking whether things are well calibrated or these probabilities are well calibrated itself is kind of impossible problem when the space is this kind of combinatorial space. So at the moment, yes, if we make model better, if we make algorithm better, if we regularize the training better, and so on, we're going to get increasingly better calibrated probabilities, which we can probably use as proxies. But I wouldn't use that for any kind of mission critical scenarios.
What about explainability? This is a question from Nadi Kim. Currently, there's increasing interest in explainable AI. Can you give your opinion on whether there be effective explainable methods for LLMs?
Oh, this is a tricky question. I gotta answer it really carefully, and then will. So in my view, explainability is too higher level concept to the point that we can't really just work on explainability. It has to be much more, let's say, grounded on the reality by having much more qualifiers as well as the setup. So for instance, one thing that, there is an example that has nothing to do with a neural network. So let's think about the smoking and lung cancer, right? And then we now know, almost everyone knows that the smoking causes lung cancer. But then there is a form of explanation. So a person smokes a cigarette and then smokes over and over. And then the smoke coming out of the cigarette contains a lot of the carcinogens. They're going to go through the person's, let's say, airway into the lung. And then those carcinogens are going to cause the mutations. They're often going to end up being a cancer. Now, okay, here comes the explanation. But at some point, if you realize somebody made a decision that the right level of abstraction at which explanation is going to be provided is a variable smoking, variable lung cancer, and then binary, and then trying to figure out the direction. It's an extremely high level of abstraction at which the explanation was provided to us. So then of course, it was a good explanation, good level, right level of the abstraction from the public policy perspective, because let's say, government needed to, intervene on the society by, let's say, creating a policy that's going to deter people from smoking in order to avoid, let's say, hospitals all, let's say, being run over by the lung cancer patients and whatnot. However, it's not really a satisfactory explanation if I wanted to work on, let's say, lung cancer drugs. Yes, smoking causes lung cancer eventually. However, that doesn't tell me how to make a drug. I cannot make a drug that's going to make people, feel bad about smoking. That seems very, very difficult. Of course, there are some people who are working on that one. So what that means is that are these large-scale language models, let's say, blessing or curse for the explainable AI? I feel like if for a very non-mission critical applications, and then where the level of the abstraction is high enough to the point that it's not going to really have a big of an impact on the individual who are seeing some of the explanation, this is perfect. Like the very fluent, it has a very, let's say, abstract notion of many different things. But if we go into more of okay, so here's a mission critical domain where we really need a precise explanation that we use in order to act on some of the, let's say, mission critical, let's say, things, then no, I don't think we can actually use it, no. So, so I guess yes and no.
That's an arguable but very interesting point of view. All right, so from Choyong-Lee. Thank you for the great talk. Since you mentioned next token prediction as a driving factor of LM, I'm wondering your thoughts on diffusion models applied to NLG. How much do you think it'll be a promising way for modeling LMs?
Yeah, diffusion models so the only place where the diffusion models have been very, very successful are where the inputs or this kind of observation space is continuous and very, very smooth. Now, some people say, well, what do you mean? Images have all those edges and so on. But still, if you zoom in, it's very smooth relative to, let's say, this kind of text, right? So will diffusion model be useful for text generation? There are a lot of, let's say, efforts. We do see those diffuser and whatnot, but it's not really easy to think of coming up with a very well-founded and highly performant, let's say, diffusion models because of the three things. One is that it's really not clear what is a good diffusion process itself that's going to have a good, let's say, limiting distribution from which we can sample very readily. So what do I mean by that is that each and every step of the diffusion process has to be small enough. So it has to be a small change so that we can easily inverse it. But then at the same time, it has to eventually converge toward the sum distribution from which we can sample easily. Turned out that the first one is often doable using some kind of edit distance or whatnot. But making sure that the convergent distribution is something from which we can easily sample turned out to be not that easy to characterize, although we can do it empirically. And then the second thing is that the text is variable length, so length changes always. So what is the right way to actually model the kind of length change together with the content change? Turned out to be a bit tricky, both for the diffusion as well as the reverse diffusion. The issue with the reverse diffusion is actually hilarious because what is the best way to tackle this kind of length change is actually to build an autoregressive model. But once we build an autoregressive model, then diffusion model simply becomes autoregressive model applied over and over, which is just heavily, heavily expensive and often doesn't actually help on top of just a one iteration. Now, there were a number of papers long ago on, let's say, trying to build an encoder-decoder model and put them together next to each other and then make the second one, refine the first one's output. It gave us, let's say, tiny, let's say, improvement. And that's the reason why no one uses it, because it turned out that we could make the first one twice as large and it just works as well. So there was no reason to do so. So the diffusion model for the text or this kind of discrete sequence generation has a number of issues, but obviously some of them will be addressed. But it's unclear to me whether some of these things are going to be addressed and end up being better than the autoregressive models at the moment.
Okay, here's a question from Ki-Hong Ho, who is as far as I know, security researcher. Someone who's more on the theory side of CS. So thanks for your great talk. If we compute everything exactly using a superpower machine with infinite memory, super fast CPU, then where is generalization coming? Because it sounds a bit ironic that creative sentence generation comes due to computational limitation.
Oh yeah, Matthew, this is a great point. But it's not computational limitation, by the way. Yes, we can always have the infinite amount of compute, but as I said, it's the regularization. So regularization in learning theory does not necessarily mean that we are regularized by the limitation of computation. So we often just this regularization can come in the form of the very explicit way. So for instance, you can imagine that we're going to build a bag of classifiers. There, however many classifiers we make using however much, let's say, computational power we have, we're not going to overfit that easily because they're going to actually contradict with each other, and then we end up with a better generalizing, let's say, classifier. So yeah, it's not really about the computational issue here. It's more like, how can we regularize learning better?
Yeah, so this may or may not be related from Ms. Kyunghyun Lee. Recently, the safety issue of large language models has emerged. I think that various filtering techniques are applied for the safety of LMs used in the product. Do you think that these regularizations hurt large language models' performance?
I mean, yes, I don't know if you're using it. So I've been using ChatGPT as well as I'm actually using the Bing plus ChatGPT or GPT 3.9 or something like that. I've been using that for some time. I mean, they did I call it like the media training too much to the point that whatever the interesting questions I ask, they're going to answer in the same way. And the Bing is a bit rude as well. It says that it's not really willing to continue the conversation further, and it's just abruptly stop the conversation. So yeah, I mean, there are a lot of questions here, but what I'm actually worried about is not about the regularization or the hurting the performance or the fact that these LLMs have the safety issues. But what I'm more worried about is that if say I ask some questions that I really want the answers to ChatGPT or whatever other people's say language model. Okay, so far so good. And then this language model started to answer my questions. But at what point can I tell that these answers were indeed the answers inferred from the large amount of data these language models were trained on, or were answers planted by, let's say, OpenAI? So if you think about it, because OpenAI uses a lot of, let's say, supervised data, those instruction data, in order to fine-tune these models, it's possible that in fact, I'm listening to exactly what OpenAI wants me to listen to, not what the data actually told language model to tell me. So I think that that's actually the most horrifying possibility, is that that's how all this propaganda starts and all this kind of, let's say, mess, let's say, I don't know, not brainwashing, but almost closely. So that's actually what I'm worried about much more so.
Yeah, that's very interesting. And I agree with that. So I saved this question for the last. This is from Kyunghyun, and we're almost out of time. Thanks a lot for your talk. It was really informative and insightful. I think it's interesting to see the important ideas are already presented about 20 years ago, and probably even longer than that, right? So I'm curious if you have any theories that recently caught your attention.
Yeah, I mean, I've been looking at pretty diverse set of, let's say, topics recently. I don't know, it's difficult to tell. Let me see. I mean, I've been reading a bit about, during the past, let's say, 6 to 9 months, I've been reading a bit about the causal inference and the causality a bit, because I feel like eventually we need to go beyond, let's say, this kind of offline statistical learning alone. So we need some kind of, let's say, more of an active exploration or the active collection of data. And then I feel like using this kind of language models, generate something and ask the humans for the feedback is one way, but that seems like a very naive way to go about. So what if we want to use these language models for, let's say, this kind of very expensive and difficult, let's say, experimentations and whatnot? We can't really just let it generate, run the experiment and see what happens. So in the case of, let's say, our work at Genentech, so we're working on the antibody design with machine learning. There, the one experiment or the one set of designs that we're going to send to our antibody engineering department for experimentation, it's going to cost us, I don't know, several hundreds of $1,000s for budget. And also it's going to take like anywhere between a month to 3 months for us to actually hear back any kinds of feedback. So we can't really be naive about it. So I've been looking into this kind of, let's say, optimal experiment design and whatnot. So in fact, we invited Ethan Muir from Caltech recently to hear about his work on what is the right way to design experiments, or what is the right way to propose a series of experiments that needs to be run in order to maximize the information gain as well as the output. So that kind of direction seems quite interesting. And then that actually does connect to a bit of a causal inference as well as a causality there. But I actually don't know anything about them. So I mean, that's just what I thought looked cool.
All right, so we're out of time. Thank you so much for spending an hour, and I know it's pretty late there, so thanks again. And do you have any last words to say?
No, I mean, thanks for the invitation, and then I hope to see some of the people here either in KAIST or in NYU, thanks to this NYU KAIST-NYU campus. Yeah. And thanks for the invitation again, Alice.
All right. Okay, bye everyone.